It's my great pleasure to introduce Hugo Larochelle. He's the lead of Google Brain Montreal and a professor at University of Montreal and a Canada CFAR chair. He's focusing on deep learning algorithms and he's been doing a lot of important work, and I'm pretty sure everyone in the room at one point or another interacted with one of his works. And particularly, he also did a lot of important work on meta-learning, and he started just a few more things. He started the TMLR journal, which is another new venue that I think it's a very exciting place to submit your work with. Approaches the question of publishing slightly different. He's a board member of ICML and was a program chair for iClear for 3 years in a row and NeurIPS in 2018 and 2019. And with that, I give the floor to Hugo for his talk.
Thank you so much. Thanks for the really kind introduction. Let me just put that on, and let me know online if you don't get the sound, or let our program chair / tech support know. So hi everyone, really glad to be here. Thank you for the invitation. I feel quite honored and privileged to be able to talk today. I'm really glad to see people in person and get to exchange with everyone here. About this general area where we're trying to use machine learning to solve a large scope of tasks. Since this was kind of a different kind of talk and a keynote, I thought I'd approach it a bit differently. So this is kind of a new talk for me, so please bear with me. Hopefully I'll go well. But I wanted to kind of take a step back and think a little bit about not just the field's trajectory, but my own, just presenting my kind of testimony of where I come from and why it is that I'm really excited about the current time. And also because this is a new conference, and speaking a little bit about how I think that as a community we should operate in this field and make progress. And so with that, I'll just present what I'm mentioning here as my general perspectives on knowledge acquisition and mobilization with neural nets. So I've had this research agenda of using deep learning and neural nets to solve tasks in AI. Essentially, this starts from the observation when we had the first really impressive and kind of industry-changing results with deep learning and neural nets that were really good at solving one particular task if we could collect a lot of labeled data for it. But being grounded in wanting to use these methods to solve as many problems as we might benefit from solving, well, it just doesn't seem realistic that we'd be able to solve the large scope of tasks, in particular those that are perhaps underexplored or that are a bit more down the tail of tasks that we'd be interested in by collecting large quantities of labeled data for each single ability with like a machine learning system to have. And so that's really the motivating idea here behind doing all of this research. And also, as it turns out, scientifically, there's something kind of really fascinating to explore that's largely taking into account and making the realization that there's a gap between how our machines right now are able to learn new tasks, which is from large amounts of labeled data, versus our ability as people to learn new abilities and skills from small amounts of experience. So knowing why there is this difference and understanding that scientifically in itself is really interesting. But really the primary goal is to try to solve as many problems as we can that we'd like to solve with AI systems. And this is really, for me, a long-standing research agenda. I've had a version of this slide, like copy-pasted across many years, for at least 6 years. And even before that, I would more or less have like a version of this in mind if I didn't present it in this way. And so I thought I'd just start by kind of framing why it is that I'm excited about, for me, and given my trajectory, particularly excited about the moment that we're in right now. But early on, when I was doing my PhD, we got really interested in representation learning. And one contribution that I'm particularly proud of is the work that I did with Pascal Vincent and Yashar Benjo, Pierre-Antoine Marzagol on denosing autoencoders, and where we kind of were advocating for a principle for driving good representations by learning them so they're robust to partial corruption of the input pattern. And seeing now that this idea has been pushed further by a lot of people in the community, but notably, it's kind of a core idea behind things like BERT, and we are seeing some also vision based backbones that are trained using a form of denoising. To me, is very exciting. I'm really happy to kind of see that we're, as a community, pushing this further and actually reaching levels of performance on a wider scope of tasks that wasn't possible before. And also early on during my PhD, one of the things that we explored is this idea of zero-shot learning. At the time, this was so early that we had a different name for it. We called it zero data learning. I think Joshua came up with that term. I really regret it. I really think we should have called it zero-shot learning. It's a way better name. This was early on, and I was going back to the paper, trying to read a little bit from it and try to see how it fits in the current context. And towards the end, we were saying that, and I'll just read it out, we also believe that, well, zero data learning or zero-shot learning should be considered as an avenue to extend the way machine learning algorithms are used. It can then be considered as falling between human-engineered systems, which requires a full manually specified description of a new task solution, and pure machine learning, which requires data for that task to come up with an appropriate model for the solution. And now we're talking about doing things like prompt engineering with systems that have an ability for zero-shot learning. And that is certainly something that I was hoping that eventually, and honestly didn't necessarily think we would be as close as we are today on doing things like that. And so to me, that makes it really, really exciting and really proud to have played whatever role that we have in sort of advocating for this idea. And then, and I guess Razvan sort of alluded to that, but I did some work more recently on few-shot learning and advocated for using meta-learning. This is actually following in a long tradition of research on these ideas, and certainly meta-learning has a much longer history. And then at the time was kind of realizing that maybe it's particularly effective for few-shot learning. And I wasn't the only one certainly advocating for that. There was also work at about the same time. But essentially, the idea of we can essentially frame a machine learning experience that would lead to a system being able to learn how to learn, or to be able specifically to do a form of few-shot learning is something we were advocating among a lot of people. And now we're seeing models like GPT-3 who are in a way very different from what we were exploring at the time, but in a way it's a sequential-based model. And to me, the real breakthrough in GPT-3 was to identify that actually we don't need to generate episodes as we were to define a meta-learning experience. We just need to learn it on text from the web, and that ability will emerge. And that's certainly a huge breakthrough that even myself didn't foresee, and that's really exciting. And a lot of other ideas of sort of understanding what leads to an emergence of leads to a form of meta learning, so an emergence of an ability to learn, now seems particularly exciting to work on that. And so I think this is why a conference like this makes a lot of sense right now. This is why I think there's been no better time to really study these questions collectively. We're sort of making progress that are really, really impressive. And for me, it's obviously very special to see that being somewhat connected a little bit to some of the ideas that I was exploring. It might seem weird I'm presenting all of this, but I'll make a point about that also towards the end. And in particular, in terms of thinking about how do we all, as a community, should think about our engagement and our involvement in this research agenda. But for now, what I want to talk about and the kind of message that I want to convey is that, at least with all these years, to me, there's kind of a picture that emerges in terms of how we think about training such systems that are able to solve a wider set of tasks. And to me, we can think of it as separating it into two different phases. There's one that I'll refer to as neural knowledge acquisition. So that's just whatever is your preferred way of doing this. There's a lot of them. But taking one or many sources of data and then creating tasks from that, and then using this to essentially try to embed some knowledge, sort of generally speaking, into the weights of a neural network. So, training a large language model is a form of that. Doing other forms of self-supervised learning on images is a form of that. So that's one phase. And then there's another phase, which is to figure out, okay, now we've got all this knowledge into those weights. How do we mobilize that knowledge in the form of a neural net towards a lot of other new tasks that are perhaps not really represented in the neural knowledge acquisition phase? And I guess part of the point that I want to try to convey today is that I really do think that there's work to be done in both sides of this dotted line. And I think there's a lot of narrative that, and in a ways I can understand where it comes from, that puts a lot of emphasis on the part on the left, the neural knowledge acquisition. It's obviously very foundational in being able to then do the next phase. But the next phase also is perhaps the methods we use today are perhaps not the ones that we'll be using later on. And also what's nice about the other phase, the neural knowledge mobilization phase, is that it's oftentimes in terms of resources actually more approachable. There's, I think, a lot to be explored there. And to put the money where my mouth is, I'm actually going to give you like 3 examples of papers that I think falls in that category. I've not worked so much more recently on neural knowledge acquisition kind of methods. I've worked much more on the latter, and I found that just as motivating. And hopefully a lot of people here would be interested in contributing in that area. All right, so the 3 pieces of work that I'll talk about are these 2 recently published papers and one that we just put on an archive. And I'll start with the first one, a universal representation transformer layer for few-shot image classification. So this is work that I did with Will Hamilton when he was at Mila, and an intern that we had recruited, Lu Liu. She did all of the work behind this paper that we published at iClear last year. Okay, and so for this work, and in a way also the next one that I'll talk about, the kind of problems we'll be solving are image-based problems, specifically image classification. So we're interested in taking some neural net, some sort of form of a neural net that's captured a lot of information from a lot of sort of source domain data in some way or another. And we want to leverage that to solve some downstream tasks, that's the term sometimes I'll use, or test tasks, such as this one, and specifically tasks that are few-shot in nature. That is, there's little amounts of data in the training set. So in this illustration here, you have a 5-way classification problem. You have 1 image per class. And what we're interested in is a system that can take the training set here and then produce a classifier that we can sort of then apply and deploy to solve the same problem on new images. And in this case here in our experiments, this is represented by an explicit test set for that particular task. All right. And so, and again, we'll be in this setting where we will assume that actually there's already a lot of useful pre-trained neural networks that are available, and what we're interested in is just how to extract information from it so that we are better at solving the downstream task of image classification. And here we'll be building on this notion of a universal representation in computer vision. This is something that's been advocating by several, but the term I think comes from Akan Bilen and Andrea Vidaldi. And it's the idea of having some representation. I think originally it was mostly thought of as having a representation that's a vector representation, but that could be useful for any possible task downstream. And then there was some follow-up work on sort of leveraging this idea, and this is an example of doing that, where actually we're quite inspired by some work by Nikita Dvornik. And so here we're going to assume that someone has already pre-trained not just a single neural net, a single representation or backbone as we'll call it, but multiple ones from different sources. So maybe there's a backbone that was trained on images of handwritten characters, another one on bird species, and another one on common objects. And what we want is to take care of the other phase, which is given a new downstream task, how do I leverage that information to do better on that downstream task? And the way we decided to represent that process of leveraging that background neural knowledge acquisition phase is that we would think of it as a process that's represented by a form of transformer. We'll have a query, we have keys, and we have values. Specifically in this setting, we think of a query being the training set of that downstream task. So the information should be contained from that. That's all the information really that we have about that downstream task. And so we'll treat that as conceptually our query. And then the keys will be the different pre-trained backbones that we could decide to retrieve for solving that downstream task. And then the values that comes with those keys, they're actually the function that gives us for a given image a representation from the pre-trained backbone from that source, for that particular backbone. Okay, so we're effectively taking a training set, our transformer is going to look at the different pre-trained backbones that are available and kind of give us a function to give us a representation that's adapted to this downstream task. Okay, that's the rough outline of what we're trying to do, and I'm going to try to provide a bit more details about this right here. So the particular architecture we went for looks like this. I'll use this illustration of, in this case, this is a two-class classification problem. I have a training set for, with 2 training images of waxcap and 2 others of fly agaric. And then from that, I want to retrieve what is the right backbone for representing images in that domain, and to be able to do image classification for these 2 classes. And so in this example, I'll just assume we have 4 different backbones. They're the 4 colors here. And when we're doing a forward pass in this model, we'll take each image on my training set and it will pass it through all 4 backbones. Then we're going to, and this is one design choice we made, we decided to do a retrieval that initially started looking at, for each separate class of this task, what is the right backbone to retrieve. So this is why we'll start by getting an average representation of each class by just taking the average backbone representation for each of the backbones. And so this is represented by that here, and the f of S1, it just essentially means the representation for the class 1 or class S1. And then we'll use the the scale dot product attention mechanism to figure out which backbone to retrieve for each of these classes. And the way we'll think about that is that we'll think about, again, the query is essentially should be represented from information in the support set. In this case, we'll actually use this average representation of each backbone concatenated one after another. And then for the key, we're actually only going to look at the representation for each individual backbone. So we have 4 pre-trained backbones, so we have 4 keys. And the key for one backbone is just the average representation of images of that class under that backbone. And then we'll feed that through the regular parameterization of scale.product attention. That is, each of the query and key will project that using a linear transformation, take the scale.product, and then apply a softmax. And that will give us, for each class, an attention score over each of the 4 available backbones. And so these will be weights that sum to 1. And conceptually, if one of the attention score was 1, the others would be 0, and that would be literally just picking a single backbone and ignoring the others for this particular class. And so we do that for each class, and then we average to get scores that are common to the whole task. And so now that gives us the final attention scores that we can use to get representation for any image under that domain from which comes that downstream task. Notably, we now have a way of representing what is any new test image to also classify it. And so again, that will just be the convex sum of all of the representations from each backbone weighted by the corresponding attention score. So this is a soft attention mechanism. If we add a 1 for just one backbone and 0 for the others, this would be just selecting a single one. In practice, because we represent that with a soft attention, then it's actually a linear combination of those. But conceptually, I think the concept still is useful to think about as retrieving a backbone. And so once we have that representation, we can feed it into a particular few-shot classifier. In this case, we use a prototypical network. And that allows us to connect that with the loss and then to train the transformer layer on episodes that will generate to learn to retrieve the right backbone. So in this case, in the sort of second phase that we're in, which is the knowledge mobilization, we're actually going to do a little bit of training before we get to have a way of actually leveraging pre-trained representations. And also, because this is a transformer and we have kind of a nice sort of conceptualization of what transformers can do, we have this notion also of having multiple heads and having multiple views or attentional views on some keys and values. And so in this case, what this would mean is that we could potentially retrieve more than one pre-trained backbone and its representation for a given downstream task by just using the concept of attention heads. And this is what we did here. So I just illustrated an attention for a single head, for a single representation. We actually found in practice that 2 is better. And when we have 2 attention heads, we just concatenate the corresponding representation. So we're going to be constructing a representation for the downstream task by concatenating 2 effectively concatenating the representation of two backbones. All right, so I won't actually go in the specifics of the results. We evaluated it on metadata set, which was a benchmark that we proposed for evaluating few-shot learning research. And at the time, this was state-of-the-art results, but this is a while ago, so now there are better results out there. But what I mostly want to convey is this kind of approach that I think is interesting. And one thing that I like presenting when I talk about this work is what the attention heads actually learn to do when we meta-train them to do this sort of on-the-fly backbone construction for a downstream task. And so in our best model, we had two attention heads. So we have two maps here. Each map, what it shows is the different columns are a different backbone that was pre-trained, that was given to us. And then the different rows are just a different domain from which I could have a few-shot classification task. In this case, we separated the tasks into, even for a given domain, into the data that was used for pre-training the backbones and the data that can be used for constructing a classification task from that domain. And we made sure that the classes were separated, so we get some form of class generalization. We also had two other data sets that actually were not part of any of the training sets of the pre-trained backbone. So we have also some sort of domain generalization happening. And so one head, and the number that's shown here is on average for tasks from that domain, what was the average attention score for the corresponding backbone? So what it shows is that this head here, what it learned is to actually always retrieve the right backbone from the right domain for a task that also came from that domain. So for ImageNet, it retrieves ImageNet backbone mostly, from OmniGlot, mostly the OmniGlot backbone, and so on. And then for the other ones that are different, that are from different domains, it mostly uses it leverages more of its soft attention ability, and it mostly uses the ImageNet backbone. What's really interesting is what the second head is doing. It's doing something complementary, and that actually kind of makes sense. So for instance, for OmniGlot, and so the other head was retrieving OmniGlot, but then the second head is retrieving QuickDraw, the backbone trained on QuickDraw, and QuickDraw is also a bunch of different concepts that have been hand-drawn. So that kind of makes sense. It sort of captured that this is a useful other representation for tasks from OmniGlot. Also interestingly, for aircraft, it liked to look at birds as the second backbone as opposed to ImageNet, which intuitively makes some sense. And a lot of the tasks otherwise, often it likes to look at ImageNet, which also makes sense. We know it's a pretty generic data set. But for some of these downstream tasks, actually it's too specialized, and you need to sort of take into account other pre-trained backbones. Okay, so to me, what's interesting about the idea of you might have a relatively structured and complex structure for all of the neural nets that have captured some sort of knowledge through some form of pre-training, and actually treating the problem of knowing where to read into this large sort of almost ecosystem of neural nets is, to me, something interesting that we could explore further. In the context of having a really large neural net that's actually a single one, we could imagine actually making the pre-trained backbones that are mentioned here just different parts or subsets of that large neural network. Maybe it could just be layers or things like that. Something we've not done but could be explored. We explored that idea of looking at intermediate layers in the next piece of work that I'll talk about, using another approach that is actually much simpler, and that I want to talk about next. So this is work that was led by Utku Evci, who's a member of my group at Google Brain Montreal, in collaboration with Vincent Dumoulin and Mike Moser, which just appeared at ICML as a long oral. Okay, so the motivation for this other piece of work, and the method, we call it head to toe, which hopefully will make sense when I describe it. We were trying to bridge the gap between a method that's relatively computationally inexpensive, like linear probe, which corresponds to doing transfer learning by just training a linear classifier on the training set of the downstream task, on the top representation of the, say, the pre-trained backbone. In this setting, we'll assume a single backbone, which will be ImageNet. So that is a very simple method. It's also very cheap. That's why a lot of people use it. It's a good way of evaluating perhaps different methods for doing neural knowledge acquisition. But also, as it turns out, it's not that good. And the really baseline that everyone should have in mind when they think about this kind of transfer learning setting is what I call the pre-train fine-tune paradigm. That is to just take the initial weights that were found in the first phase of pre-training as the initialization for more training on the downstream task, even a small training set of the downstream task. What's surprising, but has really emerged from all the research, is that even when the training set is small in the downstream task, this framework is actually surprisingly effective and doesn't overfit as much as we would think. And so we're kind of interested in trying to understand that. The problem with fine-tuning is that for every downstream task, you need to instantiate the full network that is just initialized from the pre-trained weights. If you have a lot of downstream tasks and your pre-trained network is really large, which we think is probably what we need ultimately if we want to use this neural acquisition phase to really put a lot of background knowledge in those models, we probably don't want to instantiate a separate neural net for every downstream task we're interested in. And so we wanted to try to get to the performance of something like fine-tuning, but at the expense of something closer to linear probe. I'll just add a few more data points on what I've said. I mentioned you have this graph here of the different performance of different methods when they are using some pre-training on ImageNet, and then they're doing transfer learning on tasks from a lot of different domains, which come from the VTAB benchmark, which you might know about. Here the tasks have been ordered by something we call the domain affinity metric. The domain affinity metric here is just looking at what is the performance of doing linear probe transfer learning minus the performance of doing training from scratch on that downstream task, so initializing from random weights. And the idea is that this would be high if there's a close affinity between the kind of data you use for pre-training and the kind of data you have in the downstream task, because then pre-training would have led to a representation that is close to what's useful for that downstream task, because the domain are close, and therefore the representations, we'd expect them to be close. And so we would expect linear probe to work well then. And then training from scratch would probably be just as well or worse, in particular worse if there's not a lot of data in the downstream task. So it's kind of a useful way of ordering a bunch of different domains and tasks using that fairly simple metric of just comparing the performance of linear probe and of training from scratch. And what we find is that things that have relatively low domain affinity are things generated from essentially synthetic data. In the middle, we have, so remember that here the pre-training is done on ImageNet, so we have medical imaging, we have satellite imagery, and towards the right of this plot, which is more the task coming from domain that is considered more similar to ImageNet, we have things like Caltech 101 or PETs, which we know represent the kind of images that also tend to find in ImageNet. And so what you're seeing here, you can see this gap between linear probe and fine-tuning. Linear probe is the dotted line, and then fine-tuning is the solid line here. And you can see it's essentially always better to fine-tune than to actually do a linear probe, okay? So we'd like to close this gap. And our hypothesis that we wanted to essentially test out, or the thing that inspired the method that we looked at, is that perhaps when we do fine-tuning, we're not completely transforming the representation, but all we're doing actually is exposing, sort of roughly speaking, some information that is somewhere inside the network, but that just hasn't made its way all the way up to the top layer. The linear probe approach only uses that and doesn't get to see that information, but perhaps fine-tuning kind of does this. It sort of creates new path for that information to be available at the top layer. And when you do fine-tuning, you add a head on top, and then you get to predict classes from that. So it has the ability of sort of bubbling that information up. So that was one hypothesis, one speculation we made. And so we thought, well, maybe if we have a version of a linear probe, but that gets to read anywhere into the pre-trained model, maybe that would actually get closer to fine-tuning, and that would sort of give at least some credence to that hypothesis of the role of fine-tuning. And so the method is really, really simple. Instead of doing linear probe, we have a fixed backbone here, and then weights that are added and trained on the downstream task by just reading out the top layer. We're actually going to have a head that can read from any internal hidden layer of the pre-trained model. Now, this could lead to a lot of overfitting and a lot of parameters as well. If we have a lot of parameters, we lose the benefit of linear probe versus fine-tuning, because I mentioned the sort of cost of having to store each classifier. So, and also, obviously, if we start overfitting, then that's completely useless. So we're going to heavily regularize that linear classifier that reads into a bunch of layers using some form of sparsity-inducing regularization. And what we do find indeed is that thanks to that, we first improve substantially on linear probes. So you have the performance of head to toe, our proposed approach, and the performance of linear, subtracted by the performance of linear, and generally over the line of 0. In particular for tasks that come from domain that are quite different from pre-training on ImageNet. So those domains that perhaps are not well represented by the top layer representation of a pre-trained backbone on ImageNet. So it does seem to have found some use into these internal hidden units. And also, and I'm showing numbers briefly here, where we use as the architecture for the backbone a ResNet 50, we do have that on average, the performance between head to toe and fine tuning is about the same across all of these tasks from this VTAB benchmark. And in particular, it is shining particularly well on the so-called structured set of sub-problems in VTAB, which a lot of them are essentially synthetically generated images. So again, quite different from ImageNet pre-training. And so it does look like there's some information that has been captured in the pre-training, but it was just not necessarily readily available at the top layer. But giving the possibility of the model to access it now sort of brings it closer to something like fine-tuning. But in terms of training that's required for solving each of these downstream tasks, it's less than 1% of the floating point operations and less than 1% also of the storage of the corresponding classifier. So it's a benefit from a cost point of view. Okay, and I'll move to the last paper I wanted to talk about as a method that I think of falling into this general category of neural knowledge mobilization. And we're going to shift gears completely and talk about another type of area, which is the area of code and code completion, where now the kind of neural knowledge acquisition that was done in the first phase is going to be more in the form of training a large language model on lots of data. So the problem is code completion that we'll look at here. So imagine you have some code here and your cursor is right here and you want to complete that line or you want a model to complete that line for you. So we can kind of simulate that setting by taking existing code and randomly picking a location in the corresponding file, which is what we've done in our experiments. And so here, we know that in the original file, we have this piece of code here. So we'd like the model to predict that. And the way that this has been done, in particular recently with a lot of success, is to train a large language model on some text, but also a lot of code, and then have it use the preceding context, which I'll call the default context, fed to a transformer sequential model, and then have it produce the link here, which we'll refer to as the target hole. And so that works really, really well. But we were trying to think about how can we leverage this really big and expensive models as train to make it better without doing any retraining, but providing some information that perhaps it is currently missing by just leveraging its general ability to reason about code. So notably in this example, where I have this file, affinity-propagation.java, this file falls in a repository. And in that repository, there's also somewhere else a maximizing GIP sampler.java file, which has a definition of the class and the different methods under that class. And so presumably, that would actually be useful if we could just expose that information to our model. So notably, there is this one method here, initialize to assignment, which happens to be what needs to be predicted next. So we would like to find a way of providing that information to our model so that it figures out that this might be the right thing to predict. But it's not actually straightforward necessarily how to do this because it's in a different file and it's also in a different context. So the thing we wanted to explore is, what if we just add some pieces of code that is actually found in other parts of a repository, and we just add it to the prompt that we'll feed to our language model. So we have the default context, which is the preceding code, but we also add other things that we think might be useful for the large language model to kind of reason about what should be the next piece of code to add. And so this is what we explored in this work. And if you're interested in learning more, I'll say a few words about this, but it's right now on archive, and I should say this work was led by Disha Srivastava. This is a PhD student co-advising with Danny Tarlow, and she led all of this great work. So now so let's explore this idea, or maybe I should say that if I present it in this way, it might seem obvious or somewhat obvious that it should work. In particular here, I chose a setting where I'm adding exactly what we know should fall next. But you think about it, what I'm doing is I'm providing inputs or prompts to the large language model that are probably quite different from actual code. In particular, some of that piece of code might not be consistent. I'm taking it from another file or another context. So it's really not obvious that in a way I'm asking the language model to really generalize out of distribution, because it will have never seen something like this code really, because we just pieced it up together without actually thinking about the semantics or the syntax even of that programming language. So that was kind of something we were interested in doing, and which again I see as like trying to sort of extract even more from what we think we've had this large model that was pre-trained captured. Okay, so now if we're going to add more context and effectively kind of try to design a prompt, we need to decide, okay, well, what's sort of the parameters that determine how we can construct new prompts. And in particular, in this setting for coding, well, we need to think about what is the location of the context from which we'll bring code into the current prompt. So it could be elsewhere from the current file, but it could also be from the parent class, from the file of some of the imports, a sibling file in the same repository, and so on. So we listed a few that made sense. And for each of these contexts, we also need to consider what kind of code we would extract from it, because there are a lot of different codes, different places in those files. So it could be all the identifiers, type identifiers, field declarations, and so on. And so we think of that as sort of representing the family of kinds of ways we could construct a prompt for a given location that we're trying to do code completion. And obviously, we would want to kind of automate the selection of what is the right place and the right kind of context to add into the prompt. All right, so the way we did this is that we started with Codex and used the API to just get a sense of what is its basic performance. We evaluated on a set of repositories that were extracted not from GitHub, which was likely part of the training data for Codex, but from Google Code, the public kind of GitHub-like code repository. And we took all of the repository that didn't have a name or a equivalent repository in GitHub to construct our test set. And we looked at taking various random positions into different files of all of this testing code. What is the success rate of completing a line? And the success rate is really, did you get exactly that following line? It's actually pretty high, so very good performance, as we know from the Codex paper and the recent development in that field. And then to try to get a sense of what is the opportunity, we designed an oracle, which for any given of these predictions, we'll consider extracting from one of these locations and particular type, designing a presented prompt, and then looking at, for all of these possibilities, is there at least one that actually is successful at producing the right prediction when it wasn't without that augmented prompt. And we do get a significant boost in performance. But obviously, that's an oracle. It's a performance when you get to actually see what is the answer. However, now from doing all of this, if we do this from some small subset of training data, what we can do is then train a neural net to actually predict what will be the success of looking and inserting code from different locations and different types. And we can use that as a learning signal for another neural net that would just figure out for this default prompt at this particular location, where should I look for code and what kind of information should I also add to my prompt. So the question is, will we just fall back to regular Codex performance or will we actually improve? And in fact, we do. So the two different lines here are just two different neural nets that is looking at the different architectures for predicting which location and which type of context I should add to the basic prompt. And the fixed rule is kind of a baseline where we just take the single location and type that tends to be the most successful and always use that one as opposed to changing the kind of context, location, and type that we'd add into or use to augment the prompt. And that actually already works quite well, but we do get a boost from actually being more flexible and adaptive for different situations. All right, so another example of a kind of work that focused on how do we leverage that information captured by large pre-training on different data, in this case in the form of a large language model, but that allows us to sort of move forward and get better systems. Okay, so I'm approaching time, and we'll move to questions soon. So I just wanted to wrap up and finish with some concluding remarks. So I try to make a case for this perspective, which is to think about the way we are as a community trying to solve a larger scope of tasks using AI and deep learning, that we can think of it as having two particular phases, the neural knowledge acquisition phase and the neural knowledge mobilization phase, and that they're equally valuable to work on. And notably that this one is actually oftentimes more approachable as a researcher who might not have the same kinds of resources as in big labs. I think it's important to work on both, but I think this one is perhaps a little bit too overlooked or almost dismissed. And so I wanted to advocate that actually very valuable. And I myself is actually engaging in that kind of research. And I'll just finish with a few sort of parting words where I want to talk less about what is this we could do individually doing our research and trying to make progress on our research agenda of solving a large scope of tasks with deep learning and AI, and talk a little bit more about how should we do that as a community, how should we think about that, or at least how I think about it, and you can sort of use your best judgment to see if you agree with me on that. So for me, the way I approach this as a community is first as this being an endeavor that's engineering first. And what I mean about that is that we're really trying to solve problems that are anchored in a particular sort of societal goal. We're trying to make the world better, trying to design tools that are useful. So engineering, that's using scientific notions to design artifacts and machines. And I think that fits very well with at least what has drawn me into this field. And sort of the science is kind of serving the purpose of this goal that we set ourselves in terms of improving our society and so on. That is in contrast to just thinking about, oh yeah, reproducing natural image, human intelligence in the machine is just something we should do because we can do it and that would be interesting and fascinating. And I find that less appealing. I find that if it's not grounded in some societal goals and we don't have these goals in mind where we do all of our work, that we might not be as productive. We might actually go in areas that we shouldn't be going. So I think this is something, at least for me, that I like to advocate, where when we're in this area of solving lots of tasks, where we often find ourselves talking about AGI, and that oftentimes ends up being the topic of study. But I think the topic of study is just the problems that we want to solve, and we should really first keep those in mind, I think. And I would encourage other people to borrow that mindset. And also, I think of it as a community first endeavor, and not so much as a researcher first endeavor. What I mean by that is I really like to think of what we are doing collectively, not as different labs competing or different researchers competing to make progress, but really as a community that has, incentives, it has an infrastructure, it has a way of interacting with itself, and the outcome of all of these choices that we make is progress on this research agenda. And any contribution from that community is actually progress towards this research agenda. And there are a lot of reasons why it makes sense to think about it this way. I mean, competition is a good mechanism for getting the best out of a community, but it's not the only one. And I think it's good as we're building this community to think about those as well. For instance, there are only so many things we can explore, but our resources, such as compute, also people and time, is somewhat limited. So obviously sharing as much as we can in terms of the models that we train and creating an ecosystem of these models that we can reuse, I think is good. You might have seen me talk about this concept of recycling deep learning in other talks. And I do believe that if we're in a setting where we want to solve a lot of different tasks, then we should, in some way or another, and oftentimes indirectly, just share as much computing as we can. And I think one of them is just sharing pre-trained models with one another. And also that allows everyone else to be more productive, I think. And in terms of using people's time and just the size of the community as much as possible, then just nurturing a community where we share ideas as much as possible, as quickly as possible, and in a way where we reward doing that as much as we can, I think is a good thing. And my involvement in doing things like TMLR that Razvan mentioned is not just because I think of it as it's good community service for my machine learning community. I think it's also, to me, a way of making sure that as a community, we progress towards this research agenda that I really care about and that I think is ultimately a goal in itself that can manifest itself in just the type of work we do as a reviewer, as an area chair, an action editor, and so on. And I think people just think of that as that's just a separate community thing that I do, but it's actually part of, if you think of all we're doing as a community endeavor, it's actually part of our research in the real way. And I would encourage people to think about it this way. Okay, so So essentially what I'm trying to advocate is to really embrace the collective nature of the research that we're all doing. And part of why I started with just listing some of the things I did early on and how it connects to what's happening now is that I try to do this myself. And even you might have seen some of this work and think of it, I make a connection between GPT-3 and some of the meta learning work that I made. Maybe you didn't see this connection before, maybe you don't even think it's valid, but I personally kind of make it, and that motivates me. I take a little bit of ownership of that, and that really is a motivating factor. So I think that contributions in general of any size, even those that fail, if you communicate and you share it, you're moving us all towards that objective. And so again, to me, this is another aspect of why I think it's important to think about this as a collective endeavor and find opportunities to sort of build and nurture that community in this way. I try to advocate that you don't always need to do large scale work to actually do work that has an impact, that moves the community forward. I mean, in many ways, if you look back at some of the early papers that I worked on, there were no way on a large scale setting. We're doing, variations of MNIST experiments, but some insights, were obtained from that, and that also moved the way we think about these problems. The final implementation of these ideas was very different, and the people along the way who pushed these ideas have also a lot of credit and should take a lot of ownership of that progress. But I like to think that even just feeding our collective brainstorming as to where we should go, that in itself is a meaningful thing to do. And also, whenever we try to, and I think it's tempting, and it's also tempting for me to think about like, okay, we really should strive to the large scale if we want to make the biggest progress. I think one thought that is a little bit humbling, and I always go back to, is that today's large scale is really tomorrow's small scale. So small scale work has to matter. Otherwise, everything we're doing now is meaningless to like 5 years from now, 10 years from now. And so either, you kind of accept that, but I think that's a mistake, because that means we're really all wasting our time. Or you accept the fact that actually, well, what we're doing right now, maybe it influences the kind of things we'll be doing later, and that is actually important. But let's say you do want to work more in this area of neural knowledge acquisition, this general sort of kind of problem that you might be looking at. I would encourage people to maybe pick other problems that are a little bit more overlooked. One of them that I'm trying to shift a little bit my research towards has been to do some of the work in the area of satellite imagery. And the goal that I'm grounding this into is to try to develop tools that allow for doing some environmental monitoring. So looking at what is the impact of climate change in terms of the kinds of species and how healthy the ecosystems are at different parts of the earth. And that satellite imagery is only a subset of the kind of imagery you could get. We've seen in the results that I presented that it's relatively different from what ImageNet is. And also, again, it's grounded in this particular goal that I'm hoping to achieve. I think it's the best way to get the best systems. And also, again, there's fewer people working on it. So in a way, it's kind of certainly a less stressful area to work in. And there are tons of other problems that are a bit different, where you can do a little bit of exploration of this paradigm of doing general acquisition of knowledge and then mobilizing it. And I encourage you to consider that, developing a community and a set of researchers with norms and benchmarks, and to pursue those as well. All right, and with that, I'll stop here. Thank you very much. And I think I have the set of questions on Slack that's open here. I can take those, and I can take from the audience. Thanks.
Yeah, I think, of course, the question with respect to me is there any theory behind it? Are there any guarantees, even under some assumptions? And I think one of the things that impressed me here is that if I didn't get you wrong, you showed that even training on image data on medical imaging can help you with ImageNet, or it doesn't. Mm-hmm. What are the connections that we have to assume between? So that's one thing in the context of theory. And I think more specifically, are you aware of any examples of failure that I trained on something that was not relevant, and then when I tried to do future training, it failed? Mm-hmm. Which leads to my third point, which is society. Mm-hmm. We don't share failure. We only share successes. And I think it would be very useful if people would only share will be a venue to share failures and not just successes, because we repeat the same failures because we don't know someone else already tried and failed.
Yeah. Okay.
So it's the theory of the repeats.
Yeah. I think those are great questions. Yeah, and obviously thought about those things quite a bit. I have to repeat the question, yeah. So I guess the first question is about any theoretical guarantee, I guess, in terms of when can we do that transfer sort of effectively, and how can we think about that, and how useful that could be. Then are there examples of failures where we would think that it will actually work and it doesn't? And then finally, like, what's the right mechanism as a community to kind of share these failures and sort of learn from those? So in terms of theoretically characterizing the situations where transfer learning works, I really don't know, honestly. Like, to me, it feels very much like a problem that's grounded in the reality, like almost more of a practical problem. Let's just say I have no envy for the people who do theory and want to tackle this problem with theory, because it sounds really, really hard. That means that there could be something really groundbreaking, super influential, that might actually sort of be connected with practice and in a way that's really meaningful. I think that's possible. I'm not a theoretician, so any new result from theory is a huge surprise to me. So I would not discourage that work, but I think it's really, really hard. Which might be what people need to know for them to actually start tackling it. And in terms of failures, I mean, honestly, I haven't kept a track record of when I thought transfer should work and it didn't, but it's definitely happened a number of times. And that goes to the third question, which is how do we kind of share these failures? The problem is always you don't know whether it's because the failure is that this will never work, or the failure is that the actual specific way in which you did it does not work. And this is why publishing failures is always hard, is that someone comes in and like, I think this should work. If I had done it, I think it would have worked. So I'm not sure I really believe your results. And that sounds maybe too cynical from the person on the other side, but I can kind of understand this. I mean, I've worked with students where they're like, I think this would never work, and they come back with results. I'm like, I'm surprised this works this well. And then I keep asking poking questions like, okay, well, what if you look at this? And I keep thinking, they'll find they have a bug, and then that'll be the end of it. And then sometimes it isn't. So how do we address this? I'm not completely sure, but I think when at least like it requires a commitment to certainly sharing your code and your experimental setup, so at least your specific failure is reproducible. Because an idea that works is easy to reproduce, because presumably it means it works in many settings. If you code it a little bit differently, it will sort of work. Like ideas that, I always like the term, ideas that want to work, which are these big ideas we keep using, which this is a term that I heard Jeffrey Hinton share with me once, which I find really useful. There are ideas that want to work. So those are the ones ideally we want to publish because they're reproducible more easily. And then, but failures, sometimes you don't know whether it's just the specificities of the library you're using or things like that. In a way, TMLR is for me potentially like a way to go towards that. It's important for me, it was really important for all of us, the editors-in-chief, to make TMLR not so much an assessment of how significant is whatever you're presenting, but more like, can you make scientific claims and back them up with evidence that is convincing, irrespective of how impactful this will be. And we're making progress with that. It's been really interesting at TMLR. Some people don't have that as their reflex, and we have to correct them. We look at like reviews and even the AE's sort of summary of it, and we're like, well, you're using things like significance and novelty, and these are not things we're assessing. So we need to, like, there's a reflex that we need to correct, which takes time. But I would like to think that a format like that, a company probably at least with like reproducible, code and things like that, might allow us to make progress. But still an open question, but I find with TMLR, and I was pleased with hearing the way that for CoLLAs the reviewing has been approached. I think this is the right direction, at least. I think this is part of the solution. So I have no questions on Zoom. So if someone wants to ask a question here.
Thanks for the talk. So assuming the number of backbones keep growing in size and amount, methods like the first one you presented will nicely scale or nicely produce better results, but inference time will also grow as well. and maybe you don't want to fire 100 GPUs when you do inference time for an application. So do you think we should start thinking about reducing the amount of compute we use at inference time in the way we evaluate mobilization?
Yeah, so I guess the question is about, well, you mentioned having multiple backbones. So if we actually had like an ecosystem of backbones, that might start being really, really expensive. I think that's a really interesting question. Like we should have that in mind, obviously. And I think a lot of times we don't. And sometimes that's useful if we're just exploring ideas, but that is like something that we need to have in mind. Part of the motivation behind head to toe, which is using a sparsity inducing regularizer, is that we did want to like have a model that only looks at subsets of the available representation. And we can use ideas from structured sparsity to even force it to say, decide to completely ignore a particular backbone if not enough neurons from it are actually useful or things like that. So I think that should definitely be part of the design. What I like about this approach is that it is much more, like we can distribute that much more, like a bunch of separate groups can essentially contribute a backbone and can think about the design of it. But it has the disadvantage we just talked about, which is that, well, that maybe doesn't scale. That's the advantage of instead the model where we just train really, really large model in a single infrastructure. And in a way, like, even for these groups kind of, accept the fact that we're going to use most of our compute for this because I think it's going to be useful for many other folks or, not customers, but like people that would sort of leverage that pre-training. I think there's a little bit of there's some tensions here. Which model would work best? I'm not quite sure, but I see pros and cons and I can't quite sort of call one like theoretically even superior. Thanks for the question.
Thanks a lot, Hugo. One question I have is on the, I forget the title of the work, but on the reusing backbone. I like the concept of basically attending to pre-trained predictors. There you make a specific choice. So the reason I think it's quite interesting is it moves attention from data points to attention from predictors and functions. So to do that, you need a representation for your function. And there you kind of put under the rug or very quickly that you use this average representation from data points. And I'm curious to hear whether you tried other things. I'm surprised this works because the average representation is the training to be meaningful. And so what else have you tried? And can you explain?
Yeah. I mean, so the question is, I guess I didn't quite emphasize the importance of what is the representation of the query and I guess the keys as well for representing, the keys represents the functions and then the query represents the task from its training data. And I'm using the pre-trained backbone to kind of drive this, but potentially it's one representation amongst many, I guess. So the way we converged on that, I'm trying to remember all the experiments we did, but the way we ended up converging on this is that it's essentially like available. The backbone is there. It is a window, a perspective on how you could numerically represent both the training set and the backbones themselves. It is kind of interesting, like the representation of the backbone is actually also a function of the training set. You would think that maybe the way you represent the function is by something that's not grounded in data, that's just a representation of the function. I think you can almost think of this as kind of a hack in the sense that, well, this is a representation of the function, but as it pertains to this particular task and this particular training set. Could you have some more interesting representation of the functions that's a little bit more generic or universal and not necessarily like a function of the training set of the downstream task? That's a really interesting question, which we haven't explored. In a way, like, yeah, we're sort of surprised that just doing this was working pretty well. There was work before that kind of like suggested that this was already close to a good solution, but I think this could be interesting working on this particular part. So I agree that like there's some potentially strong assumptions we're making as to like how should we represent functions. Yeah, thanks, good question. And we're probably out of time, I think. Do we do another one? Okay, cool.
So just have two quick questions.
Sure.
Thanks a lot for your nice presentation. layers and how many layers you incorporate through your let's say classifier. That's question one. Question two is you talked about knowledge acquisition and also knowledge mobilization. And do you think this pre-training would be a barrier for mobilizing knowledge from networks, or what's your impression?
Yeah, sure. So for the first question is about how head-to-toe actually works in terms of how it actually ends up selecting different parts of a pre-trained backbone. So we just treat the head-to-toe head as a linear classifier, and we add a regularizer, which is essentially a sparsity-inducing regularizer, a form of group sparse norm where we essentially have L1 penalty on the weights, or a form of L1 penalty on the weights. And we have kind of a heuristic to go about this so that it's efficient, which looks like something like training early on to get a sense of what are the largest weights, and then picking only the largest weights, and then only training on those. There's more details in the paper if you want, and the code is also available. And here in this case, you can really like select one neuron from one layer, another at another, and we didn't do structured sparsity. We tried structured sparsity that was more interesting, such as completely blank out the full layer if most of the neurons are not useful. Interestingly, somewhat disappointingly, I was hoping there was that kind of structure, but that we didn't leverage in a way that was beneficial. And we do, to go more into the details, we do things like taking the activations and applying first some average pooling, because some of the convolutional layers are really big and too big to even work in that space, even with a linear classifier. This is where like there could certainly be some improvements, but like essentially doing some average pooling on each of the layers and then just feeding all of those concatenated features to a linear classifier, that has worked like really, really well. So, and then the last question was you said using pre-training for knowledge mobilization. Yeah, I'll interpret there's a version of what you're saying that I think maybe fits, which is that some people have done things like looking at the training set of the downstream task and first doing a phase of some sort of self-supervised learning. And there's definitely some work that shows that this is better than just going straight to fine-tuning. But I think this is going to rely a lot on the size of the downstream training set. If it's really small, will some sort of self-supervised learning even a little bit be useful? I think there's work there. I wouldn't be able to kind of summarize the state of it, but that is an interesting kind of problem to study. There's some evidence that this can work well. How robust is that? I'm not quite sure, but that seems interesting to me. Should I stop here? Yeah? All right. Thank you, everyone.
Thank you.